Hey, in the last class we studied the Euler-Lagrange equation based on the action principle. So least action principle states that the equation of motion for a physical system is achieved, can be derived if we minimize the action. Then action is a time integral of Lagrangian. And we briefly consider further regarding the Lewis theorem that is related to conservation theory. If the Lagrangian has some symmetry, if you make a transformation, the Lagrangian remains unchanged. In that case, we say Lagrangian has a symmetry. If we shift the variation, you shift the position by a finite piece all over the space, we call it as a translation or transformation. On the translation or transformation, free particle Lagrangian is invariant. The result is that the linear momentum is conserved. In case of rotation, if the origin is placed at the heavy particle and another particle is moving around under the gravitational field generated by the heavy mass, then the potential energy is a function of radius that is invariant on the rotation. In that case, the potential has a rotational symmetry. If the potential has the rotational symmetry, we shall find that the angular momentum is conserved. Okay, first of all, we first consider the translational symmetry of Lagrangian for a free particle state and derive the linear momentum conservation by making use of the Lewis theorem. This is the Lagrangian for a free particle. Free particle does not experience any force. That means minus gradient force is a minus gradient of potential energy. If the potential energy is constant, then the derivative, spatial derivative, the gradient kills the constant term to find that the resultant force becomes zero. So if I add any constant to the Lagrangian, it does not make any sense because the Euler-Lagrange equation is related to all of the derivative of Lagrangian. Constant piece in the Lagrangian does not contribute at all to the final equation of motion. So we simply write the Lagrangian of a free particle to be the kinetic energy only. As I told you, if I write down the Lagrangian, it must be expressed in terms of velocity instead of p squared over 2m. P squared over 2m is the form of the kinetic energy for the Hamiltonian mechanics. Let us introduce a spatial translation by delta x for the position x. For the whole space, for any x, I give a constant addition. This c is an arbitrary constant vector. So delta x is c. Under this translation, the variation of the velocity is by definition velocity of the variation. And the variation is given as a constant piece for all x. The time derivative of that variation is vanishing always. All right. Although x has a variation, we find that there is no explicit x dependence in the Lagrangian because the potential energy is vanishing in this case. So this effect does not contribute at all. And this effect, it might give an effect, however, because there is a kinetic energy piece. However, this constant translation does not have a contribution to the velocity variation at all. So velocity variation is a zero. That means the Lagrangian is invariant under this spatial translation. So delta L equals to zero. But one can write down in this form delta L over round xi and variation of xi plus the variation due to the velocity is computed by the partial derivative of Lagrangian with respect to xi dot multiplied by the variation delta x dot. As we already have seen, this delta x dot is actually zero, even though delta x is non-zero. So this one is vanishing completely. Now we have delta x here. Let us see this round L over round xi, delta xi. And delta xi is ci. This ci is not zero anymore. It is just a constant, non-vanishing. It is arbitrary constant. So we have something multiplied by ci. That means L is a partial derivative with respect to x1 multiplied by c1 and c2 and c3. This sum is zero for any constant values for c1, c2, and c3. In order to satisfy this identity for arbitrary c1, c2, and c3, all of the coefficients must be vanishing. That means L is the partial derivative of L with respect to any coordinate is vanishing. Thus, it is a cyclic coordinate. x1, x2, x3, everything is a cyclic coordinate. Therefore, if I substitute this one to the Euler-Lagrange equation, what I obtain is time derivative of a conjugate momentum is vanishing. Therefore, every pi is constant. As a result, we have seen that if there is a symmetry in the Lagrangian, there is a conserved quantity. If there is a spatial, translational symmetry of the Lagrangian, the result is the linear momentum is conserved. Next, we consider the rotational symmetry. This potential, this central potential, is depending on the position, but the magnitude of position from the center. So this UR, if I rotate this coordinate, this UR is independent of angle, independent of solid angle, independent of polar angle, independent of azimuthal angle. It depends only on the radius. That means it has a rotational symmetry. We shall find that our final result will be the angular momentum will be conserved. The translational symmetry gave us the linear momentum conservation, but in this case we have angular momentum conservation in the case of rotational symmetry. Let us make a finite rotation, infinitesimal rotation about an axis n hat by an infinitesimal angle epsilon. This one can be obtained by making use of the Rodriguez formula for finite rotation. If I compute the magnitude of this vector, The square of this vector is x prime squared is x squared and plus 2 times epsilon x dot n hat cross x plus epsilon square n hat plus x squared, something like that. But we find that this is a triple scalar product. X appears twice. So the same vector, triple scalar product that includes the same vectors, that whose volume is collapsing. Therefore, this one is vanishing. And the only non-vanished contribution that is different from the original magnitude is over epsilon squared. In the limit, we consider the infinitesimal case, we neglect epsilon squared consistently. Sure, if we make use of the finite rotational formula for coming from the Rodriguez formula, this epsilon square or high order piece does not appear at all. It is exactly vanishing. Even though we make use of this expression, because let us recall that this natural exponent is a limit n goes to infinity 1 plus 1 over n to the nth power. If I add a higher order piece such as 1 over n squared or cube or something like that, this contribution vanishes completely. So neglection of epsilon square in this derivation does not affect the final result at all. So in a consistent way, if we consider the correction up to order epsilon, this epsilon dependence cancel exactly. So the radius is invariant under rotation. Let us introduce the Lagrangian of this central force. And this, as you know, this kinetic energy, this is invariant under rotation. This is a scalar. R is invariant under rotation too. Variation of the position vector, delta x vector, should be the difference of x prime and x. The difference is epsilon n cross x. The ith Cartesian component of the delta x vector is the delta xi and epsilon n cross x I. Let us consider the variation of the Lagrangian under this transformation. Variation of the Lagrangian can be made by taking the derivative with respect to the coordinate and the variation of the coordinate, plus the partial derivative of Lagrangian with respect to x dot I and variation of x dot I. As we already stated, variation of x dot, variation of the velocity, is actually the velocity of the variation. All right, let us substitute this result. In here, we find that the variation delta xi is epsilon n cross xi. As usual, we follow the strategy to find out the coefficient of Euler-Lagrange equation. We pull out this derivative outside and take the time derivative of this momentum, conjugate momentum, and variation. This is variation, summed over I. And the term time derivative of momentum should be subtracted, and the variation of the displacement will be multiplied in here. If I combine the variation piece into a single term, this one has the factor of Euler-Lagrange equation. As we know, this system is a mechanical system that satisfies the Euler-Lagrange equation because it should minimize the action. So the remaining piece is this one. this remaining piece is delta L equals total time derivative of product of linear momentum and variation. If we substitute this variation of Lagrangian into the formula for the variation of the action, we find that the variation of action is integral from T1 to T2, and variation of Lagrangian is substituted, and this total time derivative is removed, and the argument is placed in here. This is the conjugate momentum, so I have replaced this one with the pi, and sum of y means it is a triple scalar product, p dot n hat cross x. And because time is integrated out, this one T2 should be substituted and subtracted by the value at t equals T1. The triple scalar product can be reordered in a cyclic way, so I can move this momentum P by exchanging with n and x twice. Exchange of two factors twice does not affect the sign. Therefore, it is epsilon n hat dot x cross p. X cross p is actually the angular momentum. Epsilon n hat dot L evaluated T2 minus epsilon n hat dot angular momentum evaluated at t equals 1. We know that action is minimized. This one is exactly 0. And we know we can factor out this arbitrary infinitesimal angle and arbitrary angle n hat multiplied by this one. Should be 0 always. So arbitrary angle and arbitrary angle and arbitrary vector scalar product with something equals 0. That means that this vector should be 0. If this vector should be 0, then that is angular momentum evaluated at T2 and orbital angular momentum evaluated at T1 is exactly the same. That means angular momentum is conserved. Thus, the rotational symmetry of this Lagrangian guarantees that orbital angular momentum is conserved. This is the two major applications of the Lader's theorem. So, if the Lagrangian has a symmetry, then there is a corresponding conserved physical quantity. Okay, next we consider the calculus of variation. The action principle makes use of the calculus of variation. The action, which is the time integral of the Lagrangian, is actually a functional. Functional means a function of a function. X is not a number. X is a function. I substitute a function and get a value. Let me read it through. A functional is a quantity which is determined by a function or a set of functions. Let us consider functional capital F of f. For simplicity, we assume that f is a function of a variable x, which varies in the range. In the case of action, we used coordinate x as a function. These were functions. And integral was over t. But sometimes we can make an integral over x from x1 to x2, and this is function. For example, f of x. squared plus g of x plus dx df squared, something like that. I don't care what it will be. So this is the integrand of this function, and we can say this is a functional of f and g and their derivatives. Okay. So when I evaluate this functional, I vary this function from original value to the function variated from the original value. G of x is transformed into g of x plus delta g of x, something like that. And this one is varied. We remember x is varied to x plus delta x. X dot is varied to x dot plus delta x dot, where delta x dot is dt delta x, right? Something like that. This x behaves like t in the Lagrangian formalism. So this one, this derivative, this just like x dot, is plus variation of this. And variation of this derivative of function is actually the variation of function, derivative of a variation of this function. Okay? This functional is very useful if we consider the variation of the function to minimize the functional. For example, if I want to find the length, this length that connects the two points, I can introduce, this is x and this is y, and this y called f of x, and this curve is a function of x, and what I want to do is to find out the minimum value for the distance. This kind of problem is geodesic problem. Here, f of x is arbitrary, but I don't know what satisfies the minimum value for the distance. But distance itself is just a number. So this number is a functional. The distance, let me call distance f, is from A to B, ds. And ds is a function of this f of x, right? So I want to find the style of the function, then minimize this functional. Then exactly the same method that was used for the derivation for Euler-Lagrange equation, in order to minimize this integral, that is exactly the same as the Euler-Lagrange equation for the action, because equation of motion was to minimize the action, time integral. Okay, let us find a simple example of geodesic on the two-dimensional plane. And as you know, you already know the answer. It should be a straight line. But this one can be proved by making use of the functional theory, variational calculus of variation. Let me introduce the starting point and ending point. And the coordinates are A1, A2, and the final point is B1, B2. Let me choose an arbitrary curve connecting these two, and the distance will be the sum of the arc length. The coordinates on this curve will be expressed in x and y should be a function of x. All right. So therefore, the arc length is the sum of the square root of x direction in displacement, infinitesimal displacement, and the y direction differential. If I rewrite x1 to be x and x2 to be y, then this one should be an integral over dx, x and y, integral over dx, and the square root 1 plus derivative. All right. Although I integrate over x, for the time being, let us make use of the similar notation as we used for the action principle and Lagrangian mechanics. Then the integral was over time. So let me replace this dummy variable that is integrated out. So x is to be replaced for the time being as a t. Then dy over dx, this derivative is with respect to x means with respect to t, so y dot. Therefore, although it is not an action, let us make use of the similar notation. Action should be time integral from the initial point a1 to final point b1, and the square root 1 plus y dot squared. So it is just like Lagrangian. Lagrangian's time integral minimize. Then, if it were in Lagrangian, what we have to do is to find out the Euler-Lagrange equation and substitute this Lagrangian to that Euler-Lagrange equation to find out the equation of motion. That equation of motion is satisfying this delta S equals 0, the minimum. We want to find the minimum value for extremum, but it is evidently minimum. All right. This is the Lagrangian, and the variation of the Lagrangian should be made by first taking the partial derivative with respect to y and the variation of y. Because we have fixed the starting and ending point, variation should not be made at both ends. That's quite similar. It is exactly the same as the case of the Euler-Lagrange equation for the mechanical system. Next one is to take the derivative of time derivative of y and multiply this one by the variation of the velocity. And variation of the velocity is actually the velocity of the variation. And we require the minimum value for this action. Then Euler-Lagrange equation can be used. This is a function of y and y dot, and L as partial derivative with respect to y subtracted by conjugate momentum time derivative. By the way, we do not have explicit y dependence in this argument, in this integrand. We have this one is equal to 0. Therefore, this conjugate momentum is 0. Conjugate momentum can be computed by taking the derivative of this with respect to y dot. That is 2 times the square root 1 plus y dot squared multiplied by the this derivative of this with respect to y dot, that is 2y dot. So 2 cancels, and this is the conjugate momentum. So this one can be solved, but we have another way to solve this problem. We find that there is no explicit time dependence of this Lagrangian. If the Lagrangian do not have time dependence, we can make use of the second form of the Euler-Lagrange equation, and that is the total time derivative of the Hamiltonian. Hamiltonian is the velocity multiplied by conjugate momentum subtracted by Lagrangian. Sure, and the Hamiltonian should be written in terms of conjugate momentum instead of velocity. So at the end of the day, we have to replace that, but it is not a mechanical problem, but we want to find the shortest arc length. So just let us make use of the result. The conjugate momentum here is this one, and substitute this in here. We have a Hamiltonian to be y dot here, and conjugate momentum y dot over square root 1 plus y dot squared. And then Lagrangian, this is the Lagrangian. I substitute Lagrangian in here. I combine these two terms with the single denominator. It is a 1 plus y dot squared, and this is y dot squared cancels, and this one is minus 1. So Hamiltonian is constant because L does not have a time dependence. If this is constant, it is manifested y dot is constant. Y dot is constant. Actually, this is y, time derivative of y. But actually, we have replaced this x with the time. But actual one is not a time, but x. So we replace this one by y dot by dy over dx at the end of the day. And dy over dx is constant. That means y is a straight line. All right. Another interesting application of the calculus of variation is to find the electrostatic energy, the minimum value for the electrostatic energy. The electrostatic energy is, because we do not consider the magnetic field, the electrostatic energy is just inside of some finite volume is 1/2 epsilon 0 electric field squared integrate over the volume. And as you know, if you consider electrostatic potential V to be phi, then minus gradient phi is the electric field. Minus gradient phi, the electric field is substituted in this formula to find that gradient phi squared. So if I consider this one to be the Lagrangian, in the case of action, the integral of Lagrangian is over time only. However, we have a kind of Lagrangian. It is not a Lagrangian at all, but we have this analogy, Lagrangian analogy, is a function of x, y, z, and their derivatives, and integration over the space. So dx, dy, dz, dx, dy, dz, or dx1, dx4, dx1, dx2, dx3, something like that. All right. So this L is 1/2 epsilon 0 and gradient square. That is round phi over round x1 square, round phi over round x2 square, and round phi over round x3 square. This Lagrangian is a function of phi's partial derivative with respect to x1, x2, and x3. This is so it's too busy. So let me write in detail. So delta L is, it has a phi dependence. Actually, no. So if it would have, in general, it should have phi dependence. And then it does have this dependence. So and variation of this. Previously, if we vary Lagrangian, it should be a function of x and function of velocity and variation of velocity. And we replace this variation of the velocity to be time derivative of variation, right? Here we have x is to be replaced with the phi. X dot is replaced to be this analogy. Therefore, just like this, what we can do is delta x1 is the variation of electrostatic potential partial derivative of xi outside. So this xi here we had t, but we have three counterparts, x1, x2, x3. This is the different feature. Alright, then we can rewrite. Here we use this kind of method. Time derivative of momentum and variation, and subtract this one with time derivative of momentum and pull out the variation. And then we combine these two. These two like this, and the total derivative piece. Just like this, what we next have to do is, this one is the same, but I pull out this derivative outside. Then copy this one. And then put the variation in here. And we need to subtract unnecessary piece. And the variation. And we have two similar pieces. Delta phi dependence can be collected. Plus this. we shall find that this one to be integrated over the space. Action. Okay. So if I look at this total derivative matches one of these three variables. And then after that, it will be pulled out. For example, if it were 1, it is x2, x3 integral. But we have x1 mean x1 max. This one means the boundary. On the boundary, the potential, we do not allow the variation of the potential. So this kind of contribution all vanishes. And the only thing is this. What we want to do is find out the minimum condition for this electrostatic energy for any variation. So this one is 0. So that means this coefficient is 0. That coefficient is this one. And that coefficient can be evaluated. So if let me call this one K. First, chain rule. Take this derivative 2 times. And this one is actually the Kronecker delta, Ki. Therefore, this is epsilon 0, Kronecker delta Ki, this. And Kronecker delta can be summed over. Now we substitute to the Euler-Lagrange equation. Equals 0. You know that from this one is 0. It does not have explicit phi dependence. So this one is 0, and this one is this. This one is this. So minus epsilon 0. Zero. This is Laplacian phi equals 0. This is the solution for minimal value for the electrostatic energy. Okay, we can go further with the functional that depends on many functions. If A is a functional, if A is a functional of f1 to fn, and the integrand is f1 to fn and their derivatives, then variation of this integrand can be made with f's variation and f dot's variation. As we already stated that f dot's variation is f's variation's velocity. We have been repeating a lot. The integration by part can be used in such a way. So this one is the coefficient of the variation of each function, and this total time derivative. After the evaluation total time derivative, there will be surface term that satisfies the boundary conditions for the variation of every function. So that all vanishes. If this integral is minimized, then this variation should be 0. And if the variation is 0 for arbitrary variation, the coefficient must be 0. That means this is the Euler-Lagrange equation. So another application is a Brachistochrone problem. Brachistochrone problem is to find out the find out the path of moving a particle from A to B under gravity. There is a gravitational field, and this is a starting point, and this ending point, AB, and we don't know what is the shortest path for the time. Shortest path explicitly is just a direct straight line, but under gravity it is accelerating. And what we want to find is the minimum time to arrive at this point. This is related to the determination of function y of x, then minimize the time. We can make use of the conservation of total mechanical energy. This direction is y, downward, for parallel to the gravitational field. The kinetic energy, and it departs the origin without velocity. Then the total mechanical energy conservation states that the potential energy is completely shifted to the kinetic energy. The velocity at point y is v equals square root of 2gy. We can construct the functional t. T is sum of differential time, and sum of differential time is measured with distance, arc length divided by velocity, and velocity is determined in such a manner. And if we substitute these values to the arc length, it is just like what you have done just before. And this is the integral, this is the action. So let me replace x with the t, just like Lagrangian can, and y prime with y dot. Then this one becomes a Lagrangian. And what we want to find is to minimize the time. So let's say it is the action, minimum action. Then the Lagrangian's Euler-Lagrange equation should be satisfied. And here we have y instead of x, so we replaced y and y dot. Partial derivative of Lagrangian with respect to y and y dot are obtained in such a manner. However, the equation is quite complicated to continue. Instead, we do not have explicit time dependence in this integrand. If I make use of this, then I can make use of second form. Second form is the time derivative, total time derivative Hamiltonian is a minus partial time derivative Lagrangian, and actually this one is 0. Hamiltonian is computed in a very simple way, and this is a y dot, and this conjugate momentum. Conjugate momentum is obtained in here. I substitute here and subtract the Lagrangian and combine the two pieces together. What I find is this one. And actually this is constant of time. Therefore, this is constant. This constant means if you study further, that constant is exactly that one reproduces the cycloid. And cycloid is actually the trajectory of a point on a rim of a circle when it is rolling. Okay, let's take a rest. In the remainder of this class, we study the Lagrange's undetermined multiplier. Suppose that we have a mechanical system of n variables. We have n positions and n velocities to describe the Lagrangian. However, in case we have some constraint among these particles or positions, mechanical variables, we have some constraint. Therefore, the number of independent variables are not n, but the number of independent variables is n minus 1. Therefore, if we derive the equation of motion, we apply the action principle, least action principle. If we apply the least action principle to derive the equation of motion, we obtain the Euler-Lagrange equation. The variation of coordinates are made independently, and if there are n variables, n mechanical variables, then we would have n differential equations, that is Euler-Lagrange equations. However, because of the constraint, the independent variation of the coordinates are only for n minus 1 variables instead of n variables. If we stick to the independent variation of the variable, the final result for the Euler-Lagrange equation may be wrong. So in order to solve this problem, we introduce Lagrange undetermined multiplier. This constraint equation is actually 0, but we multiply arbitrary parameter that is called the undetermined parameter lambda. Because f equals 0, any non-zero value, lambda, is multiplied to obtain, again, 0. So addition of this 0 to the Lagrangian makes this as a unchanged Lagrange, because this is exactly 0. But for the time being, we do not assume it is 0. Instead, we just inserted this one with a new variable lambda and allow the variation of x1 to xn independently. This weak method is called the Lagrange's undetermined multiplier method. Let me show you some example. I have a single particles, then it moving along one dimension. The kinetic energy is 1/2 mx dot squared. And the potential energy should be a function of x. What happens if I introduce two coordinates? It may be a single particle moving on the xy plane, but it can also be possible to introduce two particles. One particle is moving along the x-axis, and the other particle with identical mass moving along the y direction. And there should be some potential energy. If we have two variables, then the Euler-Lagrange equation for those variables are independently varied in the action to end up with the equation of motion, two equations of motion. Suppose that we have this kind of system. Two identical mass M is attached to a string, and it is connected by a pulley, and we do not consider any mass and friction. The mechanical variable here, the coordinates of the two particles are horizontal x value and vertical y value. And the kinetic energy of the two particles will be 1/2 mx dot squared and 1/2 my dot squared. Because they are connected by a string, with an inextensible string, then this distance x and this distance y must be the same. Therefore, we have a constraint that x minus y equals 0. Because of this constraint, the system does not have any independent variables. It has only a single independent variable. Because x equals exactly the same as y, once you allow the variation for mechanical variable to find out the minimum value for condition for the minimum value of action, delta x should be the same as delta y. The variation of two variables must be the same because absolutely the two mechanical variables are absolutely the same. Okay, let us introduce the potential energy. The y is measured below this level. Therefore, the potential energy is negative, minus mgy. As we go further, potential energy decreases. So minus mgy will be the potential energy. We have constraint x equals y. Okay. We know the answer for if you apply the general physics method. This system is composed of 2m, and they are moving together, so common acceleration, and the only force along this direction is mg. So the acceleration of the system can be solved as acceleration is 1/2 of mg. So 2m is moving, but only a single m is experience the gravitational force mg. That's the reason why we have acceleration is 1/2 of g. And because x and y are exactly the same, x double dot should be the same as y double dot, and they are both 1/2 g. Suppose that we introduce a Lagrangian method, and let us vary x and y independently. We expect that because delta x and delta y are the same, we cannot vary them independently. But let us just try if it is true or not. Kinetic energy of the two-body system is 1/2 mx dot squared and 1/2 my dot squared. And potential energy is minus mgy. Therefore, we have the contribution plus mgy because L is the T minus U. Let us compute the two Euler-Lagrange equation, assuming that the two x and y are independent variables. In that case, there is no x dependence, so this one is 0, and this is minus dt, and this one is the linear momentum along the x-axis. So partial derivative of x dot gives mx dot. The second one is y. We have mg, y derivative of mg, and the y dot derivative is my dot minus time derivative. As a result, this one gives x double dot equals 0 and y double dot equals g. But this is wrong. The correct answer is x double dot and y double dot is 1/2 of mg. This wrong result is obtained because we did not include the fact that delta x and delta y are both the same. This one can be done. We can vary a single variable. Just in advance, we substitute this condition, x equals y. Then the kinetic energy is not composed of the two independent variables. Instead, it is just the sum of two kinetic energy with a single variable x dot. So total kinetic energy is mx dot squared. If you use mx dot squared as a kinetic energy, we have potential energy minus mgy, but this is y equals x. Therefore, the total, this system's Lagrangian is mx dot squared plus mgx. The Euler-Lagrange, there is only a single independent variable, so we can vary a single variable x to find the single Euler-Lagrange equation. That is this one. If I take the derivative with respect to x of the Lagrangian, we find mg. And we have negative sign on it. And if I take the partial derivative with respect to x dot, the conjugate momentum is 2 times mx dot. Therefore, we find that this one gives x double dot is 1/2 of g, and because of the condition that x and y are the same, we have y double dot is also 1/2 g. This is equivalent to the result obtained by making use of the general physics course. Now, let us consider the approach of Lagrange's undetermined multiplier. Lagrange's undetermined multiplier is the method we added the Lagrangian by this amount. Actually, this one is vanishing. Shifting the Lagrangian into L plus lambda f, this because f equals 0, it does not change any contribution to the Lagrangian. But lambda f, but do not give f equals to 0, that means the system understands that all of the n variables are independently. We can make a variation for all n variables instead. But at the end of the day, we will introduce f equals 0 this constraint later, after variation. Then minimum value for the action is obtained when Euler-Lagrangian equation is achieved or is satisfied. So we modify this Euler-Lagrange equation by substituting new Lagrangian, that is original Lagrangian plus lambda f. If we substitute lambda f and consider the fact that f is a function of x1 to xn, and it's not a function of x1 dot, x1, x2 dot, and xn dot, then we find that velocity derivative does not give any contribution for the constraint. Instead, velocity contribution, the coordinate partial derivative for this constraint is non-vanishing. If we summarize this one is time derivative of conjugate momentum here, and then we have Lagrangian's partial derivative with respect to xi, that is a force, and then this contribution appears. So partial derivative of f with respect to coordinate. So if I move this one to the right hand side, you will find that this is xi. plus lambda, this one. And this is a time derivative of conjugate momentum. This is a force. Aha, this is so-called constraint force. This constraint force is the same dimension as the force, and this is the additional force to control the system to let it satisfy this constraint equation. Okay. Then we have n equations. N equations because the number of parameters are x1 to xn. And then we have finally additional equation, that is the constraint equation. So these are n plus 1 equations. Our mechanical variables are n variables, and additionally we have Lagrange's undetermined multiplier. So we have n plus 1 unknowns. So this independent n plus 1 equation with this equation, so we can solve the n plus 1 mechanical variables that are x1 to xn and lambda. All right. If you look at the variation of the action, including this constraint, we find that because f equals 0, variation of f can be found by expanding by chain rule. Just consider the variation of each coordinate and partial derivative of each coordinate and multiplied by the variation of each coordinate. But this one is exactly 0 because even before the variation, regardless of variation, it is absolutely 0 for any combination of x1 and xn. Therefore, this variation should be 0. And variation of Lagrangian, the new Lagrangian, should be variation of original Lagrangian and lambda multiplied by variation of this constraint. Actually, this is vanishing, but for the time being, as a fake, we do not let it be 0 before the end. Delta L is calculated in terms of Lagrangian's partial derivatives with coordinate and velocity. And we do the same job as before. However, this variation, this delta L, is the original variation, but at the end we add this piece. Lambda delta F piece is added here, and this is the total derivative piece. Okay, we can combine this delta x the terms proportional to the variation of delta xi. Then we end up with this vector. This variation of the Lagrangian is in here. Thus, the variation of the action is a linear combination of all of the variation pieces. So, n independent variables are variated in order to have the action to be minimized. The coefficient should be 0. So, our result for the Euler-Lagrange equation with some constraint equation is modified in such a way. Okay, so let us consider the case when there are multiple constraints. Suppose that we have capital N number of constraints, And what we can do is add the Lagrangian with a linear combination of n independent constraints. Here we have introduced Lagrange undetermined multipliers for each constraint. So there are n constraints. Then we introduce n independent Lagrange's undetermined multipliers. Whether we multiply this number or not, it is still zero, so we do not affect the value for the Lagrangian. Finally, at the end of the day, we modify the equation with the Lagrange's undetermined multipliers like this. Okay? So this should be a linear combination of the contribution coming from the constraints. Let us return to the original problem. We recall that this problem, two masses attached by a string, and the two masses are the same, but they are moving together. The answer was acceleration, horizontal acceleration of this block on the table, and vertical acceleration of this mass hanging are both 1/2 of g. And we made the wrong calculation to find that acceleration of a was 0 and acceleration of y was g. It was because we did not consider the fact that x and y are dependent. Without introducing Lagrange's undetermined multiplier, we were able to find out the correct answer by a single independent variable x. And at the end of the day, we obtained the value of y by making use of the identity x equals y. Now, let us introduce the Lagrange's undetermined multiplier to find the correct answer. Our constraint was x minus y equals 0. That is fx comma y. Okay, this one is 0. The Lagrangian we previously obtained was 1/2 mx dot squared, 1/2 my dot squared. Actually, they were the same, but we made a fake. This x minus y is actually 0, but we multiply by lambda and do not restrict x and y to be the same. Alright, then this is the kinetic energy, and minus potential energy is like that. The modified Lagrangian can be used to find out the Euler Lagrange equation. This was the modified Lagrange equation. So if we make use of this partial derivative with respect to x, this one x here, no x, so vanishing, and this one x dot, this one x dot, and then this one derivative of x with derivative of this with respect to x, so this is lambda, and this one results in minus m x double dot plus lambda equals 0. Next one is for the equation for y, and this one is mg, and this one is my dot, this one my dot, and this one is the derivative of this term with respect to y. There's a -1 is here. If I add these two equations, lambda cancels, and we find that we have additional equation that is constraint equation. Substituting this constraint equation, we find that acceleration of x and y are both 1/2 of g. That's correct. In addition, we have a lambda here. Lambda is determined to be the same as mx double dot. That is 1/2 mg. Actually, this lambda determines the constraint force, that is tension. We remember the tension is T. T is 1/2 of mg, so that this acceleration is 1/2 of g. Alright, this kind of method can be applied to solve various problems. And this problem is the same as what we have solved now, except that the masses are different. And additional problems are given here, you will enjoy the method of Lagrange's undetermined multiplier to solve the equation and to find out the constraint force. Thank you.